Hello everyone, can you hear me? Guys, can you hear me?
Yes, we can.
No, okay. Okay. Mhm. So just give me a minute to mm, share my screen. Okay, so um, today we will be speaking about the Mie problem, the scattering problem for the electric sphere, and we'll discuss the scattering problem in general. Uh, so let's start. Uh, So we have the following geometry. Just to remind you, we have the following geometry. We have we have a plane wave incident on, for example, plane wave in air or in vacuum, uh, incident on a sphere, a spherical resonator made of dielectric with some epsilon, for example. The radius of a sphere is a. And for simplicity, let's say that our incident field is zero of R, that our incident field is the following plane wave Ex exponent I K Z. Uh, we will look for a solution in spherical coordinates. So in spherical coordinates, it will be E0, Ex, Ei, K, R cosine theta, something like this. Mm, so previously we have derived the basis that will be convenient for this problem. It was the basis of vector spherical harmonics, and basically this like the short, the brief how to say this, the recipe to solve this problem is following. So the first step is we expand fields inside and outside of the resonator in vector spherical harmonics. The second one we apply, we put expanded fields into boundary conditions. The boundary the boundary conditions are just usual, so you have continuity of tangential components. So in this case, tangential components are phi and theta. And like same for Ash. And after this, we solve linear algebraic system, because when we will expand like this field, we will have the expansion will be known, but when we will expand scattered and fields inside the resonator, we will have some unknown coefficients. We will have some algebraic system for these unknown coefficients. So, and after we solve this linear algebraic system, we will have the connection of these unknown coefficients with the amplitudes of the incident field, and basically we will solve our problem. So okay, we will not solve this like problem rigorously today because it will take us a lot of time. But I will just explain to you some main steps of this expansion. So the incident field, we know that this vector spherical harmonics, they form an orthogonal basis. What this means that because functions phi lm are which are like some Bessel functions of Kr, Legendre polynomials of cosine, theta, and exponents, because these functions are orthogonal. The set of functions L, Lm of R, M, Lm of R, and Lm of R also orthogonal. It's actually not, it's like not very hard to show, but it just takes a lot of like a lot of calculations. But well, for example, you remember that all of these functions have some like exponent I m phi as this azimuthal angle dependence, and so on the interval from 0 to 2 pi, obviously if you have like some any two arbitrary functions, I don't know, L, M, and some function B, L prime, M prime, this integral will give delta M prime multiplied by some other function of R and theta. And the same can be derived for the integral over the angle theta. So these functions are orthogonal for different M and L. And also, well, basically this means that the integral of any two arbitrary functions Lm of R B Lm of R all multiplied by sine theta d theta d phi from 0 to 2 pi, from 0 to pi will be equal to L prime M prime, will be proportional to delta L prime delta M prime. And also the same integral for M dot L d omega equals to integral of M dot N over d omega equals to integral L dot M, but complex conjugated here. Complex conjugated d omega equals to 0 for any M prime L prime. Here it's like LM L prime M prime. Here is also LM, and so on and so forth. So these functions are also mutually orthogonal. And basically, if we have some field, for example, in this case, we have our incident field. If we have some field E0 of R, we can expand it in the following way. L equals to 1, because we, if you remember, we have like no radiation from monopoles to infinity, sum over M equals to minus L to L. It's ALM MLM of R plus BLM NLM of R. Then it's not so hard to find these coefficients. For example, coefficient ALM will be equal to 1 over okay, let me write in a little bit different way. For example, coefficient ALM will be equal to integral from 0 to 2 pi, integral from 0 to pi, E0 of R multiplied by M LM complex conjugated of R sine theta d theta d phi, and divided by the same integral from 0 to pi square modulus of M LM of R sine theta d phi. So, and basically the like same for BLM. So, and if we calculate these integrals, for our incident electric field, we will actually get the following expression. We will get the following.
May I ask a question?
Yeah.
How we understand these properties for M and L and N vectors?
This one?
These integrals. Yes.
Well, basically, it's like it's a set of three. You can think about this like vectorial functions. Well, they have some dependence on coordinates, and they are orthogonal in this like functional sense, but also they are orthogonal as a vectors. Well, like quote unquote. So this is basically in three-dimensional vector space, like in Cartesian, well, spherical coordinates, they are something like, in a very simple words, they are something like three basis vectors, something like this, and also they're like basis in a functional vector space. So because
As I understand, it means that they are orthogonal in L2 space.
Yes, but but it's like, well, in a simple words, to expand some vector in, for example, in like some vector in Cartesian coordinates in a basis, you need to have three basis vector in some three-dimensional vector space. You need to have three basis vectors. And in the scalar case, we have these functions which were like, if I understand this correctly, they were orthogonal in just like in a functional sense, in the same way as like sines and cosines and so on and so forth. Yeah, but here we have some vectorial functions. So in order to expand any vectorial function, we should have this like orthogonality of basis functions in L2 space, and also like in this quote unquote three-dimensional, just some usual three-dimensional like space, like X, Y, and Z, and so on and so forth. So I'm thinking about this like in a following way. Just in a simple words. Or your question was about something different.
I think it's enough. Thank you.
Okay. Okay. So so if you expand our incident field, like using this procedure, then you will get the following. You'll get the following expression: E0 of R equals to sum from L equal to 1 to infinity, EL from M odd L1. I will just explain indices here. Minus I n even L1 J. Here this EL is just EL equals to L equals to E0 I to the power L 2L plus 1 divided by L plus 1. This indices O and E, this is because here we actually have odd and even harmonic. So just to remind you, the harmonics M, for example, MLM is proportional, was created from like functions that have exponent im phi here, and harmonics odd or even lm were created using sine for odd or cosine m phi for even. So when we will expand this function, we'll actually see that the basis of odd and even functions is more convenient here because it gives like more how to say this, more brief expression. because other way we would have here like the expression will be a little bit bigger. And this index j here actually refers to the Bessel functions that we used. Here index j means that we used as this like dm, we used spherical Bessel function of the first order. And I have a question for you, why we haven't used, for example, Hankel function of the first order, or Neumann function of the Neumann function. Why we used exactly the Bessel function here? How do you think?
Because of their properties, because it's a sphere, something like this.
Because it's what?
The properties, the zeros and others.
Well, yeah, of course it is because of its properties, but what property is important? What like
The Bessel function of
Maybe asymptotic behavior.
well,
its
not
Fisher
that asymptotic behavior, but behavior at the origin, because plane wave is like it's finite everywhere, but Neumann function and consecutively the Hankel functions, they are infinite at the origin, but we need like our field, our expansion functions, these m and n functions, to be finite at the origin, because plane wave is finite at the origin. So here we used these Bessel functions because only Jm is finite at r equals to 0, and plane wave is finite at the origin. Okay. So after we did this expansion, we can actually notice one more thing, that expansions for scattered field and field inside the resonator will also have the similar structure. So for example, field inside the resonator, we can immediately write field inside the resonator as sum from L equal to 0 or L equal to 1 to infinity. I don't know, some En Cn M OL1 J of R minus DNI NEL1 J of R, because in the expansion of incident field only these harmonics are present. This means that no other harmonics will be in the expansion for scattered fields and fields inside the resonator, because these harmonics are orthogonal. And for example, harmonic I don't know, harmonic LM cannot excite harmonic L prime and M prime if only if L equals to L prime and M equals to M prime. So, and because it's like you can't excite like quadrupole harmonic using like dipole incident field, quote unquote dipole incident field, something like this. This is because of orthogonality. From the mathematical point of view, this is because of orthogonality of these functions. Like from a more physical like point of view, this is because like the same orthogonality of these eigenmodes. So it's impossible to excite one eigenmode using like field of some another eigenmode, something like this. And this is actually really simplifies our problem. Yeah, because for incident field will look something like this. And we also can write the scattered field, which will look in a similar way. L equals to 1 to infinity. E L I A N and even L1. Here I write index 1 and I will explain why it's here. MOL1 1 of R. So just to remind you, incident field in our case, incident field is incoming plane wave. It's basically its field that pumps energy into our resonator. Because of the incident field, we excite some matter of which our resonator consists, I don't know, some electrons and so on and so forth. They start to oscillate and produce electric field both inside and outside of the resonator. And basically, because we have this incident field, the material of the resonator produces fields inside the resonator and scattered field. And because only incident field has components incoming to the origin, incoming to the resonator, scattered field should be like only outgoing wave. So, and because scattered field is outgoing wave, so it's like we have this like incident plane wave, we have this resonator, we have some fields inside, and we have some like outgoing wave. The field that is produced by these atoms and so on and so forth. And because like from the basic physical principles, when something oscillates, it produces only outgoing field. Then this means that the scattered field should be also outgoing field, and this index I here represents exactly this, because it means that here, as these Bessel functions, I used Hankel functions of the first I used Hankel functions of the first order, and in this case, this is exactly due to their asymptotic behavior, because in this case, the spherical function of the first order actually corresponds to outgoing spherical wave. It corresponds to outgoing spherical wave. Yeah, it's outgoing spherical wave. And for example, Bessel function of the second order, Hankel function of the second order will be incoming spherical wave. something like this. It will be incoming spherical wave. So this is just to satisfy the boundary conditions at infinity. Something like this. Okay. So what's next? And yeah, we have our electric field and just a small task for you. We know that electric field, well, in harmonic case, electric field and magnetic field are connected like this. So, for example, for the magnetic field of the incident wave, right now I want you to take this expression, then take this expansion, and calculate the magnetic field of the incident wave in terms of this spherical vector harmonics. Maybe like 5 minutes, something like this. Will 5 minutes be enough, or you need 10 minutes? Guys? Okay, I think 5 minutes will be enough. So guys, have you done it? Well, okay, so basically, it's very easy because we know that the curl of M harmonic is Kn. The curl of N harmonic is Km. So in this case, magnetic field will be just the magnetic field is 1 over IK curl of electric field, and it's 1 over IK sum of L equals to from 1 to infinity EL the curl of M gives Kn odd L1 of J minus K M even L1 J, and basically we can just get rid of those K's, so it's like something like minus I and like default expression. And when we will take this electric and magnetic field and put them in boundary condition, we will have some like not very pleasant system, but in the end we will get the following expressions for the coefficients A, B, C, and T. For the coefficients A, B, C, and D, for example, coefficients CL will be equal to JL of X HL of the first. Here it everywhere will be this Hankel function of the first order minus HL of X JL of X it's also X here divided by JL of NX multiplied by X HL of X derivative minus HL of X multiplied by N X JL of NX prime. So basically here this expression something in
Sorry.
the
Question. We have only complex equation for magnetic field, and it's looks like some strange. And maybe we must have A, C, and omega somewhere. And then I'm not sure, but
let me check. Well, actually, the like in CGS systems, the dimensionality of magnetic and electric field should be same, because like from this equation, this guy is like 1 over R, and this guy is also 1 over R, something like this. You mean we should have C like C divided by omega or omega divided by C here? Yes? Or
yes.
what? Well, let's check when we this one is correct, yes?
Yes.
Yes, it's just from the Maxwell equation. So when we take the curl of this guy, for example, we get kn, and we also have 1 over k before, so k is like cancels out, and this actually this is logical because like as I told before, from the Maxwell equations we can see that dimensionality of E is same as dimensionality of H. Well, if we would derive everything in for example, SI system of units, in this case we would have something, we would have some proportionality, how to say this, proportionality coefficient here, like 1 over k or something like this. Also I think, let me maybe check it. Maybe you can send the expressions that you have derived. Maybe I made a mistake. It's possible.
I think it's okay.
Okay. Well, for example, if we would do this in SI system of units, we would have this proportionality coefficient. For example, in SI system of units, curl of E is I omega, and I don't know, in the general case, some mu also, and we would have something like this, that H equals to k divided by I omega mu, and this like this sum. So something like this. But in CGS, everything like is proportional. This is why it's very convenient. Okay, so this expression with square brackets, well, of something, it means the derivative with respect to argument. So for example, this expression nx jl of nx equals to d over d nx of nx jl of nx, something like this. Also, these functions functions x jl of x are called Riccati-Bessel functions. Also, this is you can find like the same function with Hankel functions and Neumann functions and so on and so forth, but it's not so important in the moment. So, and the expression for the d coefficient will look similar. It will be njl of x x hl of x derivative minus nhl of x xjl of x derivative divided by n squared. Also here n is just the square root of epsilon here, because the permeability for the sphere equals to 1. Here n is just the square root of epsilon. JL of nx x HL of x derivative minus HL of x and JL of nx derivative. So for the fields, for the coefficients of fields inside the resonator, we will get something like this when we will put this in. Also, I forgot to say that here x is what is called the size parameter. It's a multiplied by k, where a is the radius of a sphere, k is the wave number. But what's most important is actually the coefficients for the scattered field, because in this case we are interested in the scattered field more than in fields inside the resonator. And coefficients
What
for
is
scattered,
n? Sorry.
n is the square root of epsilon. Is just refractive index here.
Thanks.
So the coefficients for scattered field look similar. They're following. It's the coefficient a is n squared JL of nx x JL of x prime minus JL of x and x JL of nx prime divided by n squared JL of nx x h L of x prime minus HL of x and xJL of nx prime and coefficient BL equals to JL of nx xJL x prime minus JL of x and xJL of nx prime divided by JL of nx x HL of x prime minus HL of x multiplied by nx JL of nx prime. So if we will look at these coefficients, we will basically see the same structure as we had with, for example, reflection coefficients for the Fabry-Pérot lab and so on and so forth. We have here some denominator that has complex roots. We see that we can see that it has complex roots because of this Hankel functions here. If we had only Bessel functions here, because the roots will be real, but because we have this complex Hankel functions here, we have the complex roots. So and basically when this denominator is close to 0, we have the resonance. We can find the eigenfrequencies of the eigenmodes by zeroing this denominator and so on and so forth. And at the moment we derive these coefficients, we actually know everything about the scattered field. So we know everything. We know how this sphere. We know how the sphere scatters incident light, how much energy is scattered by the sphere, and so on and so forth. And to get all of this information, it's enough just to plot, for example, to get the intensity of the scattered field, we can just plot the sum. Well, this like EL squared multiplied by AL squared plus BL squared. This is not intensity, this is like scattered power. Just remind you, the power is an integral of Poynting vector over some surface. Let me call this surface over some surface sigma, and because of the orthogonality of these vector spherical functions, well, we know that Poynting vector has it's like E cross H real part, so it should have like some like also some terms like M N and so on and so forth. But because of the orthogonality of these vector functions, in the end we will have expression. Well, we have something like this. I will also put like proportionality sign here. And actually, there is one very convenient tool. I will now send the link to this tool to the chat. It's called MeCalculator. Maybe some of you also already know this MeCalculator. But even in this case, let me share the screen of my computer and show you this MeCalculator. Yeah, so basically what it has, here you can put the refractive index of your background media. Right now it's just 1 for the air, and here you put the range of wavelengths for which you want to plot this me coefficients. This like coefficients A and B, they called me coefficients. The coefficient A is actually called magnetic me coefficient. Coefficient B is called electric me coefficient. This is just because coefficient A is proportional to M harmonic, which is called magnetic harmonic, and coefficient B is proportional to N harmonic, which is called electric harmonic. Yeah, so basically here you put the boundaries of the domain of like in which you want to calculate your me coefficient. Here you also can choose the number like of layers. Right now we have derived me coefficients for just one sphere, but it's possible to have like core shell structures. This is one sphere, one small sphere or like big sphere, which is coated by the layer of another material, and even like this like spherical multi-layer structures, but right now we will not look at this. And for example, let us put the radius of a sphere equal to, I don't know, 50 nanometers, and refractive index of sphere equal to 1.4, the imaginary part like 0. And let's plot this modes to plot. It's actually it corresponds to L. So in this case, we'll have only L equal to 1. Here L equal to 1 and L equal to 2. Here like L equal to 1, 2, 3. This is basically the dipole, quadrupole, and octupole modes. And here you choose like different quantities to plot. Right now, you just need to know that this Q scattering is this like square modulus of these coefficients A, B, and C, but I think later in this lecture I will tell you what is scattering, absorption, and extinction stuff. And here you choose what here you choose what actually different how to say this, contributions, different contributions of different modes you want to show. So for example, if I want if I want to plot only this like mi coefficient A1, B1, then I just need to put here only electric and only dipole mode, because B coefficient is like electric coefficient, is electric mi coefficient, and L equal to 1 is the dipole. If I want also the magnetic, if the magnetic like quadrupole, it's like A2. I just need to put this here. And we can also plot like the sum of all coefficients. Here we can choose total and plot the sum of all coefficients. So something like this. For example, we can see that for a sphere of the radius of, let's run the simulation, and we can see that for a small sphere, when like the wavelength in this case is from 400 to 1000 nanometers, and radius of a sphere is 50. It's 50 nanometers, and the radius of a sphere is very small. We can see that like for small sphere there are like no resonances on so yeah. And for example, if we'll increase the radius of a sphere to 200 nanometers, we can see that not 200, maybe like 500 no, 500 nanometers. We can see that there are like some oscillations, some resonances. Maybe 100 nanometers will give us let's put 4 here, so we have like, yeah, something like this. So we see here, because we see here some like pronounced resonances, and the first resonance is actually, we see that it's H dipole. The first resonance is magnetic dipole resonance, then goes electric dipole resonance. So basically, this wavelength, it's 832 nanometers. This corresponds to the resonance of this A1 coefficient. This wavelength of 660, this corresponds to the resonance of B1 coefficients. Then it's A2, then it's B2, and like so on and so forth. So, and we can actually see, for example, if we want we have some like spherical particles, for example, some colloidal spherical particles or something like this, and we want our particles to shine bright. We know the radius of our particles, we know the refractive index of our particles, and we want to find the wavelengths at which these particles will shine like as bright as possible. We just need to calculate this scattering coefficients, these mi coefficients, and to find the position of maximal scattered power, something like this. And actually, it's also possible to plot near field. Let me. It's possible to plot near field. Here we have just like the number of points. So we plotting here we're plotting here the electric field as a function of x, y, or x, or for example x, y, z coordinates. Maybe just let me here is something strange happening. Yeah, this is like something something strange happening, but basically maybe if I just take the basic parameters here, everything will be okay. Yeah. Okay. So for example, right now we are at this wavelength. This is the wavelength of the electric dipole resonance when the B1 coefficient has its bigger value. So we see here some like, well, it looks like dipole. We have some asymmetry to this side here because the wave is incident from this side. The wave is incident like from left to right. So because of this, we have some asymmetry here. Oh, I broke everything once again. Yeah, because of this, we have some asymmetry here. So basically, you can calculate, for example, we want to look at the near field of the magnetic dipole resonance. And magnetic dipole looks something like this, or maybe the magnetic quadrupole. So, well, this is very convenient, tool if you want to calculate this like scattering spectrum of a sphere, of maybe you have some like multi-layered structures, you have some, I think I will write it, draw it to you, what is core shell and all of this stuff. So, okay, maybe you have some questions about this?
Can you repeat, please, what means number of modes or something like this when you simulate?
Yeah, okay. So, you remember? Okay, maybe let me share my screen of my iPad. I will write it to you. So, here we have electric field. What maybe let me take this scheduled field. Here we have a lot of different harmonics. We have harmonics from L equal to 1 to like L equal infinity. And we have here electric harmonics and magnetic harmonics. Oh, I made a mistake actually. This A is electric Mie coefficient, this B is magnetic Mie coefficient. Here we have like electric harmonics and magnetic harmonics. So the harmonic N EL1 corresponds to electric dipole. For example, harmonic MOL2 corresponds to magnetic quadrupole. And when you choose number of modes, so for example, here we have 4 modes to plot. Okay. Well, it doesn't matter. Sometimes this doesn't work. For example, if you want to plot like only dipole and quadrupole modes, we choose modes to plot equal to 2. In this case, it will plot as modes with L equal to 1 and L equal to 2. This like Mie calculator will actually plot. It will plot A1 squared, B1 squared, like, and A2 and B2 squared. And here, like when we choose, for example, here we have chosen, let me try one more time. Yeah, okay. Here we have chosen 4 modes to plot, and you see we have dipole, quadrupole, octupole, and hexadecapole. So here we have L equal to 1, L equal to 2, L equal to 3, and L equal to 4. And after this, we can also choose if we have some like here, some cross here. If we choose this, this will show us the A3 squared, something like this. If we choose this one, it will give us B2 squared, and so on and so forth. Okay, is it clear?
Yes, thanks.
Excuse me. So we have that our electric field is even and our magnetic field is odd.
It's not electric and
Mod,
it's
yes?
not it's not electric and magnetic field.
I know, yes, but in these terms.
Yeah, all electric harmonics are even, all magnetic harmonics are odd. But you also can see that here for all harmonics, m equal to 1. M equal to 1 for all harmonics. But this is actually only because of the like polarization and incidence direction of our like incident wave. We choose incident wave like to be proportional to EX, I, K, Z. And in this case, well, it can be clear like from the symmetry of functions, but well, in a simple words, it doesn't matter from which direction to it doesn't matter from which direction we have incidence, because we have a sphere, and obviously all directions are equal for the sphere. So for example, if you will choose some, I don't know, ikxx plus some ikyy, you will get a little bit different answer, but you will just complicate your calculations, because just by rotating the coordinate system of coordinates, we can reduce this to this. And in this case, well, you will get the answer that we have. So something like this.
So, I mean, only in this geometry we would have like n even and m odd, but in different kind of geometry we could have something more complicated, yes?
Yes. In a general case, in terms of like this odd and even, for example, we can have, I don't know, for example, our incident field is some very strange function. I don't know, it's some Gaussian beam or something like this. In this case, like the most general form is L equal to 1 to infinity, M equal from minus L to L, and it's A, L, M, M, L, M plus B, L, M, N, L, M, or also we can write this in terms of odd and even functions, sum of M from 0 to L. This will be, I don't know, let me call it alpha LM M alpha odd LM M odd LM plus alpha even LM M even LM plus beta odd LM N odd LM plus beta even LM and even LM. This is like the most general form. But for the plane wave that we have, when you will try to calculate this guy and this guy, you will get 0. Something like
And
this.
could we get something like or m being odd and or m being even by maybe some reflecting or coordinates? Because if you say that we could put all ELM and OLM as zeros, could we get something like this, but vice versa?
Well, it basically it just depends on how your electric field looks. This is basically the expansion. It is basically the expansion of your incident field in terms of some basis functions. For example, if your incident field equals to, I don't know, equals to ME 1, 0 of R, obviously you will have only alpha E01 equal to 1 and all other coefficients equal to 0, something like this. For the plane wave, when you take like the plane wave, for example, the plane wave, I don't know, with some random polarization and some random direction of propagation, with some random propagation direction, I think you should have, like, in general case, you should have all harmonics present in the expansion. But I'm not sure because I have never done it, but like from the first guess is that you should have like all functions here for some general plane wave. But for some particular plane waves, due to some like from one point of view, due to some symmetry reasons and all of this stuff, you will have only even electric and odd magnetic harmonics. Yes, even electric and odd magnetic harmonics. Something
Thank you.
like this. Okay. Okay, so basically, what we have done right now, we have solved the what is called the scattering problem for spherical resonator, and the main goal of the scattering problem is to calculate the scattering field, because we're interested in the scattering problem. We are interested, like, what will happen if we will shine some light on our object. Well, plane wave is very simple example. Of course, we can also have some Gaussian beams and all this stuff. But because we know that Maxwell equations, at least our Maxwell equations, are linear, we can calculate the scattering field for Gaussian beam also if we just take some series of these plane waves and so on and so forth. And I think let's maybe make a 15-minute break, and after this we will speak about some like more general stuff, some general scattering problem, because we could have not a sphere, we could have some cylinder or some more complicated structure. So it's right now it's 11:26. Maybe let's continue at 11:40. Okay. Okay, guys, so let's continue. Boom. So yeah, we considered scattering problem for a sphere, but the light actually can be scattered not only by spherical objects, but by some general, some cylinder or some any random shape. So let's speak about the general scattering problem. So for example, we have our background media. With for simplicity, I will consider only dielectric medias with permeability equal to 1. So we have some background media and we have some object. We have some object with some epsilon of r. So our epsilon function in this case, our epsilon function, maybe let me actually write it like chi, so it through susceptibility. Just to remind you, the susceptibility, the epsilon is 1 plus 4p here. Yeah. So our epsilon function in this case will look something like this. Epsilon of r will be equal to epsilon background. Oh no. No, actually, I want here like some delta epsilon. Some epsilon of r. So our epsilon of r will be background epsilon plus some delta epsilon of r. So this is our like our background. For example, it can be air or it can be some dielectric. And this guy is change in permittivity due to the scatterer. We will call this object that scatters light, will call it scatterer. Well, in the general case, like we can derive the wave equation for electric field. In a general case, this wave equation will look something like this. It's curl of the curl of electric field. This is like total electric field of R minus k squared permittivity of R multiplied by electric field of R equals to 0. But we also say that we have some incident field. So this can be a plane wave or like Gaussian beam, laser beam, some Bessel beam, some vortex, and so on and so forth. So for example, we have some like incident field E0 of R. We have some incident field. What actually will happen in this case? Well, I already told you before, but I want to say this one more time, that this incident field will irradiate our scatterer, and the atoms, I don't know, the meta atoms, if it's some meta surface or something like this, will be excited by this incident field, and they will produce their own field. From the mathematical point of view, we can rewrite this field. We can rewrite this total field. This is the solution of this equation as a sum of E0 of R and some other field E prime. Something like this. We can actually do this because we can rewrite this equation. We can rewrite this equation as follows. We can rewrite this as curl of E of R minus K squared E background E of R equals to K squared delta epsilon of R E of R. And we can use, for example, we can use the green function to solve this equation. And in this case, the solution of this equation will be something like this. It will be some E, I don't know how to call this. Let me call this E alpha R plus integral of the green function of R minus R prime. This will be like K square delta epsilon of R E of R prime D free R prime. So you guys know what is green function, or do I need to explain this? Sorry, can you please repeat one more time? I think the connection is not very good.
Yes, we know.
Okay.
We know.
Okay, good. So, and this E alpha is actually the solution of homogeneous wave equation. So because to solve the solution of non-homogeneous wave equation is basically any solution of homogeneous equation plus the solution of non-homogeneous equation. Yeah, so this is actually this guy will be our E prime in this case. So we can write total field. We can write total field as E0, which is our incident field. And incident field is usually, for example, when we took the plane wave in the case of scattering of a plane wave on a sphere, the plane wave is solution of homogeneous Maxwell equation. So Gaussian beam, which corresponds to the laser field, is also a solution of homogeneous homogeneous wave equation. So we have our E0 and E prime of R, something like this. And we can actually take two different regions. We can take two different regions. For example, let me call region outside of the scatter region 1 and region inside the scatter region 2. So in region 1, we will have incoming wave, which is E0 of R, and we'll have outgoing wave. In this case, it will be E prime of R should be outgoing wave, and previously we called this scattered field. We call this scattered field. And in the second region, we will have just some fields inside the scatterer. We can write field inside as some superposition of E0 of R plus some E prime of R, or we can just write it as just E inside as we done it previously. So, and from this point of view, actually, the scattered field, we can put this, we can put like this definition into our wave equation, and we can look at this from another perspective, because so it will be curl of the curl of E0 plus E prime, which is like scattered field or something like this, k squared 1 plus epsilon background plus delta epsilon of R multiplied by E0 plus E prime equals to 0. We know that this is solution of homogeneous of just homogeneous wave equation. For this is basic solution of wave equation without scatterer. So this is solution of curl of a curl E0 minus k squared E background E0. So we can rewrite this equation as curl of a curl of E prime minus k squared minus k squared epsilon of R E prime equals to k squared delta epsilon of R E0. Let me check this, and this goes to 0 because of this, and so only this guys goes here. Yeah, it should be correct. So we see that what is happening here is that this electric field, it induces some currents or polarization in the body of our scatterer, and we can actually see very clear from this that this polarization, these currents produce some external electric field, some electric field inside and outside of the resonator, something like this. And actually, when we solve the scattering problem, the main task of every scattering problem is to find this scattered field. Scattered field. This is a field that is produced by the scatterer. This is the field that is produced by the scatterer in the region outside of the scatterer. By region 1. So yeah, this is basically the field. For example, if you have some experiment, for example, we have some dielectric cylinder, and we shine the light on this dielectric cylinder, and we measure some electric field, or we measure some intensity of light in the microscope. This will be our scattered field. So this is the field that is produced by our scatterer due to some external electric field that is incident on the scatterer. But the more complicated the scattering problem, the more complicated the form of the scatterer, the more complicated will be the scattering field, and because what we are interested in is the properties of the scatterer. But sometimes it can be very hard to understand these properties just from the scattered field. So, for example, we want to know how much energy, how much power was scattered, or how much power was absorbed in the scatterer. And if we will just look at the scattering field, then it will be very hard to get these quantities, to understand how much power was scattered just by the look of the scattered field, just by looking at the functions. And because of this, people actually introduced several quantities. People introduced the quantities which are called scattering and absorption cross-section. They called scattering and absorption cross-section, and these properties are defined in a following way. The cross-section, we will let me write it. Oh, well, let me just write it like this, cross. These cross sections are introduced as the power which is scattered by the plane wave, which is scattered by the scatterer under the incidence of plane wave, divided by the intensity of this plane wave. So, for example, scattering cross section is power scattered divided by the intensity of the plane wave, which is just the modulus of the Poynting vector. And absorption cross-section is introduced in the similar fashion. This is just absorbed power which was absorbed by the particle, by our scatterer, and divided by the intensity of a plane wave. And basically, the bigger the cross section, the bigger the scattering cross section, it means that our scatterer is like scattering a lot of energy. So the scattered field has very high intensity. The bigger the absorption cross section, it means that bigger the amount of energy that was absorbed inside the particle. Here, these two guys are just time averaged powers. In the first case, it's the power which was scattered by particle. In the second case, it is the power which was absorbed by particle. And this is basically the intensity of incident plane wave, something like this. Actually, these like cross sections, they came from quantum mechanics. When people were studying the scattering of electron on the atoms, they introduced this notion of the cross section. And then it was adopted in optics. So if speaking about how we can calculate these cross sections, so we know that power in some electromagnetic field is just the integral of Poynting vector, over some surface, over some closed surface. So here, for example, we have our scatterer. We have some incident field. We have our scatter, and we can draw some surface around our scatterer. I will call the surface sigma. And to get, for example, to get the scattered power, we just need to integrate. We just need to integrate the Poynting vector of a scattered field over this. Here n will be just the normal vector. We just need to integrate the Poynting vector over this surface sigma. How to calculate the absorption, the power which was absorbed by the particle? The power which was absorbed by the particle is actually the change. This is how much energy was taken from the field. We can calculate this as a rate of this change of the energy of electromagnetic energy. So basically, from the physical point of view, if we have some energy which if we have some incoming and outgoing energy, then if we have more energy incoming than outgoing, that means that some energy is absorbed inside the particle. If you have more outgoing waves than incoming, more outgoing energy than incoming energy, it means that we have some energy generated inside the particle. So we can, to calculate the absorbed energy, we can just we can calculate the difference, like this difference of incoming and outgoing energy, and in this case, we can calculate just the integral of total Poynting vector with minus sign, because we want to calculate this like rate of the change of the energy, which is like incoming here, something like this. And basically here the scattering Poynting vector is the same c divided by 8 pi. This is like time average Poynting vector. So this is just the scattered Poynting vector is calculated from using this using only the scattered electric and magnetic field, and the total Poynting vector uses total electric and magnetic field. So do you have some questions at this moment, or everything is clear?
So with scattering cross-section, this coefficient C and B, yes?
Yeah. I will actually show you later that the scattering cross-section can be expressed using these coefficients A and B.
So, I mean, this sigma is has physical meaning of area, yes?
Yes. This sigma, this is like I will speak like just in 2 minutes about the physical meaning of the cross sections. Okay, so basically you can actually like think about these equations. If you remember, we have like a continuity equation. For example, we have continuity equation for charges and currents, and we also have a continuity equation for electromagnetic energy, and the power is the rate of change of the energy. And from continuity equation, we can calculate for example, absorbed power as change in the electromagnetic energy inside the resonator. we can, using the continuity equation, we can rewrite this. In this case, we will need to integrate over the volume of the scatterer, but using the continuity equation, we can write this just as integral of the Poynting vector, which is energy flux. Okay, but if we will look closely at these equations, we will see one interesting thing, that we can write the total Poynting vector, the Poynting vector of the total field, as a sum of incident Poynting vector plus sum of a Poynting vector of the scattered field plus some another, like, let me call it S prime, some another term. So what do I mean by this? In that the total Poynting vector is C over 8 pi real part of total electric field multiplied by conjugated total magnetic field. But electric and magnetic field is electric field of incident wave plus scattered electric field, and the same for the magnetic field. Magnetic field is also a superposition of incident electric field plus of incident magnetic field and scattered magnetic field. And if we will put these two expressions here, you will actually get that we have something like this: C over 8 pi real part of E0 times R0 conjugated plus C over 8 pi real part of E scattered times R scattered conjugated plus the following expression: C over 8 pi real part of E0 times H scattered conjugated plus E scattered times H0 conjugated. And what is actually this part? What is actually this part? So if we will integrate, like left side and right side, we will get that the left side gives us, this guy gives us absorbed power. So this will be power which is absorbed inside the particle. If we will integrate this guy here, we will get 0, because in the background field, the energy that is incoming into the volume of the resonator, volume of this scatterer, is the same as energy outgoing from this, like, from this sigma, from the volume encapsulated by this sigma. Just want to show, is it clear for you why is integral of Poynting vector of incident field is 0 or not? Or do I need to speak about this a little bit more?
Please expand because of the error which we
No,
got, because the
no.
integral of
This is yeah. In some sense, this is because we have integral over, like, closed volume. We have integral over closed volume. So you see that yeah.
if this is the same when we calculate the Poynting theorem, we have the same term, and we say that integral according to this closed area, which is infinity big, it always equals to 0.
I think yes. To be honest, like there are different ways to work with Poynting theorem, so maybe I'm not getting, but just let me explain. For our incident field is just a plane wave. Just a plane wave. So the amount of this integral of Poynting vector, well, actually, let me actually maybe write this like Poynting theorem. So Poynting theorem says to us that the rate of change of electromagnetic energy, well, if we have like no external currents and all of this stuff, the rate of change of electromagnetic energy is equals to minus divergence of the Poynting vector. Minus divergence of the Poynting vector. So if we integrate the Poynting vector over some surface, d sigma, for example, this will give us the total. This is energy density U. This will give us the total rate of the change of electromagnetic energy. But for the plane wave, we know that background field is solution without the scatterer. So just air or just some homogeneous dielectric. If we have no losses in our dielectric, which we assume, then the amount of energy that is incoming into this area is equal to the amount of energy that is outgoing from this area. So we can, like from this hand waving explanation, we can expect this guy to be equal to 0 and therefore this guy also to be equal to 0, but only for the incident field. Only for the incident field. Something like this. Is it clear?
Yes, yes, about this theorem. Yes.
Mm-hmm. Okay, so for the incident field, let me write it like one more time. We have some power which was absorbed by our particle, minus power which was absorbed by our particle, because absorbed power is calculated with minus. So we have this power, minus power which was absorbed by our particle. We have here this guy equals to 0. This guy will give us just the power which was scattered by our particle, and we have something here, something strange here, and this guy is actually called, this is such so-called extinction power. And what is the physical meaning of this extinction? In the end, we will have the following equation, that minus power absorbed equals to power scattered minus extinction power, or in other ways, that extinction power is absorbed power plus power scattered. So if we'll divide everything by Poynting vector of the incident field, like we will actually get that what's called extinction cross-section is equals to absorption cross-section plus scattering cross-section. So the extinction, basically the physical meaning is obvious. The extinction gives us the amount of power that was scattered by our particle and absorbed by our particle. This is the physical meaning of this extinction is the power that was taken from incident field by absorption and scattering processes. And this power can be calculated. This power can be calculated in a following way. So this this power of extinction is equals to minus integral of this expression over this like closed surface. But there is so like the physical meaning of the scattering cross sections is basically of that all of these cross sections like scattering, absorption, and extinction is basically the amount of power that was either scattered, absorbed, or both scattered and absorbed by our particle, normalized by the intensity of the plane wave. And so dimensionality of all of these cross sections is the dimensionality of power divided by dimensionality of the Poynting vector. And actually it is like meters squared. So this is dimensionality of area. And there is actually some geometrical interpretation of the scattering cross section. We can also introduce the fourth cross section, which is called geometrical cross section. To get like this intuitive physical meaning of these cross sections, let me consider the following problem. For example, you're outside in the streets and you have rain on the street, which is like very common thing for St. Petersburg. So you have some like rain, some raindrops falling on the ground, and you're going in this rain, you're going with umbrella. You have some you have some umbrella, and you like walking in the streets with this umbrella. And this umbrella have some area. If you will look at this umbrella from above, it will be just some circle. It will be just some circle. And for example, because this umbrella do not, for example, we have some rubber umbrella, ideal rubber umbrella, because the rubber does not absorb water. For example, this absorption cross section for umbrella will be equal to 0. But our umbrella scatters particles. In this case, the scattering cross section will be equal to number of particles. The scattering cross section will be equal to number of particles, which is like how to say this. Scattering cross section will be equal to number of particles which is like incident on this umbrella divided by like sorry, I forgot the word. So it will be just equal to number of particles like scattered incident on this umbrella. Maybe give me a second. This is basically will give us the fraction of particles scattered by this umbrella, something like this, out of like all particles. So and in this case, where it was, sorry, I can't find the correct expression in my notes. Just give me a second. Just give me a second. So for this case, because like no particles are scattered outside of our umbrella, so here the rain just drops. Here the rain just like drops on the ground. Here rain just drops on the ground. Only this area will scatter. Only this area will scatter the rain particles, and in this case, the scattering cross section will be equal just to the area of the umbrella. It will be equal just to the area of the umbrella, and will be equal to what is called. It will be equal to area, and it will be equal to what is called the geometric cross section. The geometric cross section is just basically the area of the scatterer. In our case, it's the particle. It is the area of our umbrella. So the scattering and absorption cross section basically gives us like the effective area. For example, in the case of absorption cross section, for example, we have some strange umbrella. We have umbrella something like this. But here on the top of umbrella, on the top, we have like this small like hole, something. It's not hole, it's like some cup. And when rain is falling into this cup, it stays here. So in this case, and for example, area of this cup is A0. This is like area of this guy. And the area of our umbrella is just A. In this case, the absorption cross section will be equal to this A0, and the scattering cross section will be equal to A minus A0, something like this. So, but because photons are not just like particles, photons are waves. For example, in the case of electromagnetics, even when you have some scatterer like this, and for example, your photon goes somewhere here above your scatterer, it still feels this object. Because it's a field, and the field goes like, well, in the general case, it goes from minus infinity to plus infinity. And in the case of electromagnetics, these cross sections gives you like the effective area. It gives you the effective area of your scatterer that is like filled by your photons. So for example, you can have some finite object, but the scattering cross section may be equal to 0. This means that for the photons at this particular frequency, your object is like photons don't fill your object at all. Or you can have some like very small object but very big cross section, and basically it means that this object, your photons feel this object as some like very big object, something like this. Okay, so this is basically like simple geometrical meaning of the cross sections. Do you have some questions about this or not? Guys, do you have some questions?
No.
Okay. Um, okay. So what next? We can actually rewrite, get different we can get another expression for cross sections. We can get another expression for cross sections. For example, let me start with extinction cross section. Just to remind you, the extinction cross section can be calculated as c over 8 pi divided by Poynting vector of the incident wave and the integral of the real part of E0 times R scattered plus E scattered times R0 integrated over some surface. We will now show that we can actually write the extinction cross section. We can write extinction cross section, or maybe just let me first show you for the power, just extinction power. We can write, we will show that we can write the extinction power in the following way, like 1/2 integral of the real part of the current multiplied by E0 integrated over the volume, where this guy is currents inside the scatterer. And we will be able to show this from the thing that's called reciprocity theorem. So for example, let me consider two different current distributions. For example, we have some, I don't know, some currents J1, and we have some currents.
Excuse me, could you please repeat how the theorem actually spells?
Reciprocity theorem. Maybe you had this theorem before.
I think yes, I just wanted to ask how it actually.
No, well, because if everybody had this theorem before, I will just skip the derivations. So please tell me if you don't know what reciprocity theorem is. So everybody knows what reciprocity theorem.
Can you repeat, please?
Okay. So just to repeat, we have two current distributions in space, J1 and J2, and we have some fields that is produced by J1. This is like some electric and magnetic fields that produced by J1, and we also have electric and magnetic waves fields that produced by J2. So this is like E1 H1, and these are like E2 H2. We can write Maxwell equations that govern these fields. So just regular Maxwell equations, IK H alpha and the curl of H alpha equals to I, for example, IK E alpha plus 4p divided by C J alpha. Here alpha is equals to 1 or 2. What we can do right now, we take this equation we take this equation for alpha equals to 1 and multiply it by magnetic field produced by the second current. So in the following way, we have H2, and we also like we conjugated, we have H2 conjugated multiply by curl of E1, and this is equals to IK H1 multiplied by H2 conjugated. And we do the same thing for E2. We have H1 multiplied by E2 conjugated equals to minus IK H1 H2 conjugated. And we also do the same thing for we multiplied the equation for magnetic field. We multiply this equation by electric fields in the same way. And then we sum all of these equations, and we have something like this. We have something like, oh, sorry, I made a mistake here. Here should be minus. It should be minus here. So in the end, we have also two more equations. We have E1 multiplied by curl of H2 conjugated equals to minus IK E1 E2 conjugated plus 4P over C J2 conjugated multiplied by E1, and we have E2 conjugated multiplied by curl of H1 equals to this. There should be plus here because it's conjugated. Equals to minus IK E1 times E2 conjugated plus 4P over C J1 times E2 conjugated. Okay, so let me label this equation as the first one, the second one, the third one, and the fourth one. And basically what we are doing right now, we take equation number 1, we take the first equation, and we sum it up with the second equation and with the third equation and with the fourth equation. Maybe I made some mistake. Maybe made some mistakes in the signs, but we will check it right now. So what we have here, we have H1 times curl of E2 conjugated plus H2 conjugated times curl of E1 plus E1 times curl of H2 conjugated plus E2 conjugated curl of H1. And yeah, it seems that I made some mistake. It should be, let me check. Here should be plus. Here should be plus. And here should be minus. Here should be minus. And I think that here should be minus. Something like this. Yeah. So we have minus here and we have minus here. And this is the left part of the equations. This is the left part. So we can actually use here the following identity. We can use here that B times curl of A minus A times curl of B equals to divergence of A times B. For example, this guy is B times curl of A, and this guy is A times curl of B. So we have here the divergence of E1 times H2 conjugated plus also we can look at this and this term, and we have here E2 conjugated times H1. This is the left part. For the right part, what we have here, for the right part, we have like the minus first equation. We have minus this guy. We have minus IK H1 times H2 conjugated, then plus second equation, plus second equation, boom. Have I made any mistakes here? It seems that I made a mistake. Just let me check it. Yeah, sorry. Do you want to say something? If you want to say something, I can't hear you. Yeah, I made a mistake because here it should be minus. Here it should be minus, and here it should be plus. Sorry, so this is with plus, and this is with minus. So we have here we have B minus A, and here we also have like B minus B curl of A minus A curl of B. Yeah, okay. So this will be like then IK H1 times H2, then plus the second equation, which is like minus IK H1 times H2 minus IK H1 times H2 conjugated, then minus the third equation, minus IK E1 times E2 conjugated minus 4P over C J E1 times J2 conjugated. J2 conjugated times E1, and then minus second equation. Here will be plus and here will be minus. It's plus IK E1 times E2 conjugated minus 4P over C J1 times E2 conjugated. So obviously this will give us 0, this and this also will give us 0. So in the end, we have the following expression. We have the divergence of E1 times H2 conjugated plus E2 conjugated times H1 and this equals to minus 4p over c J1 times E2 conjugated plus U2 conjugated times E1. Something like this. And this is basically, one of the forms of reciprocity theorem. In general case, you can derive this reciprocity theorem for like any two sets of Maxwell equations. So here we had just two currents in the same media, so mu and epsilon here like everywhere.
Excuse
so-
me, could
yeah.
you please switch to the place where we change our signs?
Here.
Okay.
So it's 1 plus 2 minus 3 minus 4, something like this.
Okay, yes, thank you.
And here like all equations. Okay, so here we have just like two distribution of currents in air. But in general, you can take any two Maxwell equations, any two sets of Maxwell equations. So for example, maybe let me show you the slide from the presentation of Andrei, where he actually he derived like the more general form of this reciprocity theorem. Yeah, here. So you can hear that here he has like mu1 and epsilon1, mu2 and epsilon2. Something like this. And also you have, this is what's called a conjugated form of reciprocity theorem, because you have conjugated fields here. But you can do like using similar procedure, you can derive what's called non-conjugated form, where all the fields are non-conjugated. But for us, actually, only this expression is interesting now. Only this expression is interesting now, because, for example, let us return back to our scattering problem, and let's take E1 and H1 equal to incident field, and E conjugated H1 will be equal to H0 conjugated, and E2 and E2 conjugated and H2 conjugated. Let me take them as just E scattered and H scattered. H scattered conjugated. Yes. So if you will substitute it here, we will get something like the divergence of E0 times H scattered conjugated plus E scattered times H0 conjugated should be equal to minus 4 pi over C minus 4 pi over C J conjugated multiplied by the incident field, because so let me explain the right hand side a little bit. Here this J conjugated is actually currents inside the scatterer, because well, we showed here where we showed it. Yeah. we showed here that we have that scattered field is actually produced by some induced currents. So I just want to like clear this out, that this is not like external currents. For example, we put some wire with current in our media. This is exactly induced currents, like currents induced with our inside our structure, which are connected with like polarization of our structure, and so on and so forth. So these are like induced currents induced inside our scatterer. And because for the incident field, we have no currents, because it's like solution of just a homogeneous wave equation. For incident field, current is 0. Then here we will have like I1 equal to 0 and J1 equal to 0, and J2 will be just this J inside. And if we will integrate this stuff over the volume, for example, volume given by the surface sigma, using Gauss theorem, we can reduce this integral of divergence. This integral of divergence will be equal to integral of real part. Let me also take the real part. This will be like real part of E0 times R scattered conjugated plus E scattered times R0 conjugated over D sigma. And here on the right hand side, we would have minus 4p over C integral of the real part of J conjugated times incident field over D over the volume encapsulated by this area sigma. Yeah. And if we will divide everything by, well, let me not divide by, multiply everything by C over 8 pi minus C over 8 pi. Here we would have minus C over 8 pi, this like integral over the area of this guy. And on the right hand side, we would have just 1 over half integral of real part of J multiplied by the incident field over the volume. And we can see that this guy is exactly the power of extinction. It's exactly the power of extinction. So in the end, we can derive that extinct power is equals to 1 over half integral of the real part of the currents which are induced inside our structure, multiplied by the incident field. Sorry, this should be like E0 everywhere. E0 dV sigma, where J is like total current induced inside our particle, and it equals to well, we know that epsilon is connected with conductivity, so we can write it through the conductivity. So it's basically the conductivity multiplied by the total field. This is like all currents inside our how to say this? Total currents inside our structure, something like this. But actually, this can be like more or less. We can also derive the same expression for the absorption cross section and the extinction cross section. This is like total field inside our structure. we can derive the same equations for the absorption cross-section and extinction cross-section. And in the case of absorption cross-section, we would have something like this: 1 divided over 2 integral of the real part of J multiplied by total field, total electric field, over d v sigma. And for scattered cross-section, it should be where is it? For scattered cross-section, we can actually get expression from these two guys, because extinction power is like absorption power plus scattered power. So scattered power is just extinction power minus absorbed power, something like this. Do you have any questions about this? Okay, so if no questions, we have only 10 minutes left, I think. So maybe let in the end, maybe. Okay, I think I will continue about this on the next lecture. So on the next lecture, I think that we will speak about, we will return back to the sphere. We will get this expression for scattering and extinction cross-section in terms of this Mie coefficients A and B. And I will just like explain to you some notions of what is a scattering channel, and and I think we will look at different regimes of scattering, because we have different regimes when the particle is very small or the particle is very big compared to the wavelength, and so on and so forth. So something like this. Do you have any questions? So, okay, if there are no questions, then thank you very much for the lecture, and see you next week. I think the next week will be the last lecture given by me. And after this, you will have lectures by Daniil one more time. Something like this.
Thank you.
So, yeah, thank you very much.
Thank you. Goodbye.
Goodbye.
Bye.
Thank you. Bye.